Okay, so proof of the midsegment theorem. Now the midsegment theorem is really a theorem about the relationship that exists within the same triangle. So the statement here says that if D is the midpoint of AB and E is the midpoint of BC, so in other words we have two different conditions here. So I can say that D is the midpoint of AB, so I can mark these congruent marks here, and E is the midpoint of BC, so I can make another set of congruent marks here. Okay. So if both of those conditions are met, then I can actually say two different conclusions. First, DE is 1/2 of AC. So let me just draw DE here, and DE is called the midsegment. So in other words, this green segment here is 1/2 the length of AC. And the second conclusion that I can write is that DE is parallel to AC. So the green segment is parallel to AC. Now, so this is really kind of like two different proofs, two different theorems that are very much related. So we state it together as one theorem. And in fact, the method of proof for both of these statements is going to be very similar. And I'm going to prove each of these parts one at a time. So I'm going to start by writing a proof for the first statement, that DE is 1/2 of AC. Okay? And in this proof, I introduced the concept of a coordinate proof, which means I take this figure and I draw a coordinate plane around it, the x-axis and the y-axis, and I can draw the x-axis and y-axis wherever I want. So I'm going to try to draw it cleverly so that it's going to be helpful to me to complete this proof. So I'm going to start by drawing my y-axis there, and then I'm going to draw the x-axis here. So I draw the axes here in a way that's going to be helpful to me. Got the y-axis up there and the x-axis right here. And the reason that I've drawn it this way is that I can place point A right at the origin, and I can place point C right on the x-axis. Now, when I draw it this way, it allows me to write in the coordinates. So A is going to be 0, 0. C, well, I don't really know what the x coordinate is, so I'm just going to call it P. Okay, we'll call this variables. So the coordinates here is going to be P, 0. I do know the y coordinate of point C. Let me clean this up a little bit here, make it look a little bit nicer. Okay, so the coordinates of C is going to be P, 0. Okay. I don't know what the coordinate of B is, so I have to use two variables here. We'll call it Q and R. Okay. So once I have this set up, I can actually start trying to do the proof now. And one of the first things that I'm going to do is find the coordinates of D and E. Okay. So use midpoint formula. For the coordinates of D and E. So D is, since it's the midpoint between A and B, we apply the midpoint formula to A and B. So it's going to be Q plus 0 over 2 R plus 0 over 2. In other words, the coordinates of D is Q over 2 R over 2. Let's make this Q look more like a cube. Then I'm going to find the coordinates of E. So let me write this in. So the coordinate here is Q over 2, R over 2. Okay. To find the coordinates for E, basically do the same thing again. So E is going to be Q plus P over 2 and R plus 0 over 2, or just R over 2. Okay. So now that I have these 2 points here and their coordinates, I can actually start and find the distance between E and D. Let me write the formula here. So this is Q plus P over 2 R over 2. Okay? So the distance between D and E, and here what I can do is use the distance formula, which is the square root of the difference between x1 and x2 plus the difference between y1 and y2. But if you look here, the y coordinates are exactly the same. The y coordinates for D is r over 2. The y coordinate for E is also r over 2. So that means the distance between them is just the absolute value of the differences in the x coordinate. So in other words, it's the distance, it's just the straight horizontal distance here. So this is Q over 2 minus Q plus P over 2. Okay. So we'll simplify this a little bit further. This is the absolute value of Q over 2 minus, and I'm going to separate a Q plus P, so it's going to be Q over 2 plus P over 2. Okay? And you can see that the Q over 2 and Q over 2 are going to cancel each other, so the distance between D and E is just P over 2. Okay? So this is very useful to me as well, because if I know the distance between D and E, I can compare it to the distance between A and C. So let's try to figure that out now. What is the distance between A and C? Well, you can see that the y coordinates again are the same. They're both 0. So it's just a straight horizontal distance between A and C. So this is just P, the absolute value of P minus 0, the differences between the x coordinates. So that's just going to come out to be P. Okay. Now if we compare the two of them, DE is P over 2 and AC is P. Well, that's interesting. So I can now take AC and substitute in here for P. So I can say that DE is equal to P over 2, but instead of writing P, I'm going to write AC. And so there you have it. I can say now that DE is equal to 1/2 of AC. And that ends the proof for part 1. So let's just recap here a little bit. What I've really done here with this proof is start out by putting the triangle in a strategic spot where A is 0, 0 and C is P0. I don't know what the coordinate is for C. I just know that the x coordinate, it's some variable. I know that the y coordinate is 0. And then I've done the same exact thing for the other coordinates for B. Okay? Use the distance formula to find the coordinates for D and E. And then use the midpoint formula to find the coordinates for D and E, and then use the distance formula to find the distance between D and E and A and C, and then compare them. And once I compare them, you can see that DE is just 1/2 of AC. So that's a completion of proof for the first part. Okay? Now watch the next video for proof of the second part.